Yes, sir. No joke, that one. Why the
Yes,
business
thank you.
want to please seek your indulgence to mute, and if you are recognized to speak during questions, you unmute, and when you are done, you also mute back so that we can all enjoy the lecture. Thank you for your cooperation.
Thank
Thank
you.
you
Good.
very much, ma. Paulo,
Yes.
let me bring the forward in while you take it up from there.
Yeah.
Um, Thank you once again, engineers. I'm elated to be in your midst. So, just as my profile says, I am a proponent for sustainability and green building, and I believe that we have so much uh, traces of unsustainable practice in our concrete. Nigeria, should I say, fortunately or unfortunately, our construction is heavy on concrete. How we found ourselves here, I don't know, and I don't think we'll be able to discuss that this evening in this meeting. But the reality at our hand is that our construction is heavy on concrete, and that, of course, brings in the unsustainability of using reinforced steel, which will do as the case is at the moment. Just as one of the engineers said earlier, right now, even at the federal level, we seem to be pivoting towards concrete for road, which is very good and very sustainable. But unfortunately, when we look at the element, which is the most important in that design, the reinforced steel that we use, it is not sustainable practice. And that's what we're going to find out at the end of this presentation. So on this call as well, we have engineers representing the Nigerian Building Roads and Research Institute. The essence of having them on this call is while Paulo and I are thinking of how we can bring this GFRP into our construction industry, we need to also cover the basis for testing and policy, in the sense that we know that in Nigeria, before you can build, we need to have materials tested. In fact, it is a stage certification requirement to have all our reinforcement tested at intervals. So this is why we have the NBRRI with us on this, and to also join us in this collaboration. And also, the better part of it is having engineers to know how to design with this GFRP, because what we design with the DSI 8110 does not have provision for GFRP. And we need to develop capacity for our local engineers to be able to design with GFRP if at all we're thinking of sustainable practice in our concrete. And that is why this meeting has been put together. So I will hand over the floor to engineer Dr. Paulo Casade. Please take it away from me. Thank you so much.
Thank you, Emmanuel. And let me thank all of you. It's a true pleasure being today virtually in Nigeria, even though I hope I can visit you personally very soon. I hope you see my presentation. Can you please confirm that?
Yes, we can say it.
Okay,
Yes, we
super.
can.
So um, I think today's call, I have many slides. I will hand it to you afterwards. So if I'm gonna scroll fast on some of them, I think you will be able to then reconnect afterwards. And please stop me if you have any questions or you have any doubts or any issues that you would like to stop me and go forward in explaining better. So these are I put together some pictures because unfortunately today, Nigeria, specifically along the coast or very close to the coast, obviously experiences what is experienced by any country, deterioration of concrete due to aggressive environments. Here you see columns, but you see ports. And certainly reinforced concrete, traditional steel reinforcement, is one of those construction method that is obviously present around the world, but it's also very vulnerable specifically in aggressive environments. So usually when we look at concrete structures, we always think as ways to let's say fix or try to solve the issue of deterioration, and traditional mitigation efforts usually center on keeping chlorides from getting to the reinforcement steels, like increasing concrete cover, altering the concrete mix, adding membranes, or, for example, adopting other type of traditional steel reinforcement like stainless steel or epoxy coated. But all these remedies add cost and also reduce the sustainability efforts for more sustainable infrastructures. And it's because of this that today, in order to guarantee 100 years construction life for reinforced concrete structures, I have the pleasure to introduce you to, let's call it a new family, an alternative family to of reinforcement for concrete, which is based on glass fiber composite reinforcement. Before doing that, I would really briefly allow me like 30 seconds to introduce you to who we are. The original composite company is born from the separation from Owens Corning, which is a worldwide leader manufacturer of building products. We do take care now of the composite industry with 1.3 billion revenue, more than 4,000 employees. We recently joined a holding, an Indian holding, Prana Group. We are present producing glass fibers pretty much everywhere. Unfortunately, not in Africa, but hopefully we will be able to support your construction industry. As you can see from here, we produce all different type of glass reinforcement, from knitted fabrics, woven fabrics, continuous filament, chopped strand mat, and in particularly the type of fabric that we're looking today is the continuous fiber type, which is the one that we actually transform and we make it into GFRP fibers. So what is a GFRP rebar? GFRP stands for glass fiber reinforced polymer. Basically, just like all the composite materials, which you know very well, for example, mud and straws, traditional construction method. Here we have a matrix which is made of a resin, and the end we have structural reinforcement which is made of ECR glass. ECR stands for E corrosion resistant glass. And the reason of that is we added in the chemistry of the glass substances to make it less aggressive, less attackable to alkali environment. The matrix is a thermoset polymer, which is usually either made of vinyl ester or epoxy resin. A thermoset resin is a resin that once it's cured cannot be deformed any further. I usually make the example of to distinguish thermoset and thermoplastic resins. The thermoset is the equivalent of an egg, which is fluid, and before cooking it, then we cook it, and then it becomes solid. And depending on the shape, on the form, whether it's scrambled, fried, or whatever, boiled, then that shape cannot be modified. Oh, there is a microphone open. Do I need to stop? No.
Please go ahead, sir.
Okay.
Go ahead, sir.
Okay, sorry. So the reason why the role of the fibers and the matrix, the fibers provides the mechanical performance of the rebar in terms of tensile strength and Young modulus, whether the resin provides the protection to the fibers to alkali degradation and guarantee long-term durability in addition to making really the composite effect. So imagine having all these very fine spaghetti one next to each other, and the only way that we can make them work all together is through the resin. So the resin is really the load-bearing transfer between one fiber to the other. How rebars are manufactured? Rebars are manufactured through a process which is called pultrusion, from the word pull. So it's an extrusion by which we actually pull. So in reality, the process begins from the very end, from over here, and then we basically, the operator starts first with the fibers going through a bath of resin, and then through an extruder, a die, and then here you have an heater in between, and where in the heater and in the die there is the impregnation of the fiber, and then everything is tied to the very end where there are the hydraulic rams, which really literally pull the fibers through the die. So the process really starts from the end and not from the beginning. Usually we push the steel through the die. In this case, we pull the fibers through from the die. And then this is what we have. We ended up with a bar. In our case, Mateen bar is a bar that is a technology that has been developed in New Zealand. I will not go into these details now because it's not really important. The manufacturing sites are dislocated in 3 locations in the world: in North Carolina, Saudi Arabia, and in New Zealand. The technology was developed in New Zealand, the specific technology of how we manufacture these rebars, and you can see it here. These are pictures from real sites, job sites. So again, there is a glass roving, which is our glass roving, the Advantex Light Type 30. Then there is in order to make the bar, to enhance the bond between the bar and the concrete, because steel rebars are ribbed. In our case, the roughness is provided by grooving the bar, mechanically grooving the bar, and then we have a thermoset vinyl ester resin. Now, this is how the bar is made, and you can see it better from here. So all our bars, and now I will explain you what that means and why that is important, are all CE marked. And here you see the diameters, the standard diameters, which are 6, 8, 10, 12, 16, 19, 25, 30, 25, 22, 25, 32. The bars are meet also international standards. And here you see the data sheets. And again, I want to just go through very fast. One thing which is very important, when in a job site, usually you handle steel, usually wearing gloves. Sometimes it happens that you take the steel bars with your bare hand. Now, in the case of GFRP bars, we need to be careful on that. We need always to wear gloves, because otherwise the bars leaves a very small spikes of glass, which may stick in our hands. Is not dangerous, but certainly is not pleasant to have them in our hands. The product can also be available in the presence of meshes, just like it happens for steel, making steel meshes. I don't know how much you adopt straight bars or meshes when you manufacture flat works like roads or precast panels or slabs on ground. In Europe, for example, meshes are very much diffused because they make labor faster, in laying the reinforcement on ground. We can also supply, and that's something that you have to be aware, when we talk about bend bars, and this is probably I would say, not the bottleneck, but certainly something that is preventing or is slowing the adoption of this material, and I really want to be very open and transparent on this, is the fact that because straight bars, if you remember what I told you before, remain straight and cannot be bent like it happens with steel, when we build something with the GFRP, in that case, we need to supply stirrups or any bent shape, like you see them here in the picture, already pre-sagmated. Why? Because the resin is a thermoset, so it cannot be bent and deformed locally. Okay, it has to be pre-formed at the factory site. Okay, now certainly we can work with let's say predefined shapes to make it easier, but if you have specific dimension that you need to follow, that's something that has to be specified before the order of the material. And that's is not just with us, is with any company around the world. So the technology, despite the look of the bars and despite how the bars guarantee bond concrete, are always done in the same way. What are the advantages of glass reinforcement? And I think this is where the fun begins. It's a material that does not rust, so there is no corrosion whatsoever with this material. I'm showing this picture here because if concrete, and this is something which is very important to remember, because most of the issue that we do experience in concrete durability is because sometimes, and everywhere it happens in Italy, it happens literally everywhere, we do have issues of durability of the concrete reinforcement, of steel reinforcement, because concrete is not properly mixed with clean water and clean aggregates. Now, the beauty of this material is that we can mix it even with ocean water or with sand coming from the sea and not properly washed. Why? Because the material does not corrode. And this is one of the big points by which we can guarantee more sustainable reinforcing product, because we can actually make concrete in a more sustainable way. Also, because the material doesn't rust, in specific application, like for example slab on grade, we can actually reduce the concrete cover. I know you design according to the British standards, which are very much alike the Eurocodes, or actually they're the same thing. And if you recall your British standards specification on concrete cover, we can actually reduce the concrete cover because this material does not need to have the same type of protection that you would do to a steel reinforcement. It is stronger. It is about 2.5 times stronger than steel. It's about 1,000 megapascal, but, and this is something very important, the Young modulus, the E modulus of this material is slightly lower. We're talking about 50 GPa, so 50 gigapascal, which means there is more or less 1/4 the one of steel. And this, how does this translate into design? It translates that we probably may need slightly more material when we design reinforcing members that are subjected to deflection, in order to control and to have the same control in deformations. Okay. Now, the other very important thing is the material is 4 times lighter than steel, which means that when we transport, or when we can transport 4 times the amount of steel in volume, so 25 tons of steel are approximately 4 times more material in length of equivalent diameter than in steel, which means that we can save on transportation, so we can have a less impact on CO2 given by transportation. Also, and this is something very important, in the on the job site, the labor, the people that are handling the material, will experience a much more lighter material to handle. Consider that in North America, this material has been chosen by the contractors only because it is lighter. Okay, it is chosen by the contractors because it's lighter, and so the labor goes home in the evening with less shoulder less pain in the shoulder, simply because the material is lighter. So not only is lighter and the people are happy, but it also allows speeding up the construction.
Prosper.
Yes.
Prosper.
Yes.
Prosper.
Hello? I guess I can move forward.
You can go ahead, please.
Yeah, okay. Another point which is important, may not be so significantly important, is the fact that material is electromagnetic transparent, which means it's non-conductive and electromagnetic neutral. And this makes it interesting, for example, in infrastructure, for example, like railway, where we might have, particularly today that we start electrifying all our transportation, there is not going to be any issue in galvanic corrosion given by high voltage present in around the steel, around the construction. And also, for example, in hospital, where we do have electromagnetic transparency equipment, like MRIs, for example, magnetic resonance, we do not need to protect the steel from becoming in contact with the magnetic field given by the equipment. So certainly provides several interesting aspects. Last but not least, the material has a low thermal conductivity and a no thermal cyclic impact, which means that in precast construction or in elements where, for example, in your country, certainly more exposed to heat than we are here in Europe, this makes the construction of reinforced concrete certainly less conductive, less thermal conductive than when it's made with traditional steel. And so these make it ideal, for example, as reinforcement in insulation precast panels or in any other application where insulation is crucial for the project. So just as a summary, we can transport more material for truckloads, which means we have fewer CO2 emission. It's more durable, which means that we can basically zero the maintenance on the construction sites. We build it today, and we're not going to touch it for sure for the next 100 years, which means that we certainly actually are saving a lot of money. It is safer because it's lighter, so there are less injuries and more productivity on the job site. How can we handle the material? Well, the material can be handled just like any traditional reinforcement, can be cut on site much easier than it can be cut on with steel, because it's remember that transversely it has the same shear resistance than plastic. So it just, even though I don't like to call it plastic because it certainly doesn't remind me a sustainable material, the reality is that when you handle it, it's plastic. From an engineering point of view, you have to remember that this material is anisotropic, which means that the high tensile strength that we experience in the direction of the fibers, certainly there is not transversely. So we need to, so this is an advantage when we handle it, when we want to cut it, but certainly from an engineering point of view, we need to remember that. We can tie the bars just like we do tie any other type of bars. So you can see here the people handling, imagine transporting 20 millimeters rebars by hand, 6 meters long. This guy would be a Hulk. If it was steel, it's just transporting the bars made with GFRP with no hassle whatsoever. As here you can see the tying of the bars that can be done just like any other material. Here they decided to adopt plastic coated wires, but you can certainly do it with steel, with traditional steel wire with no issue. Any comments, any questions so far?
Doctor, sir, the
Yes.
usual point allow you to be through with the presentation, then people will be allowed to ask questions.
Yeah, absolutely. Yeah, go. Unfortunately, I had the screen on, so I couldn't see. But if you prefer, ask me question now, we can certainly ask me question. Absolutely.
All right, sir. Yes, sir. So we
I see there is
distinguish.
yeah.
I want to believe we follow the lecture. So
Okay.
the presenters would like to accommodate if there is any question now. So please kindly indicate by raising your hand. I can see uh, some of us have started raising our hands. Engineer Kingsley Erifeta, please, you have the floor, sir. Your
Oh, good
question, sir.
evening, ma'am. Thank you very much. Okay, let me go straight to my question. Can you hear me, ma'am?
Yes, go ahead.
Yeah.
Hello.
Yes.
Thank you very much. Majorly, towards the last section of your presentation, you talked about the sustainability impact of GFRP. Please, can you tell us a little about the fire resistance of this material, the fire resistant capacity of this material? Because I did hear you talk about that.
Yes, very good question. Okay, let me answer very rapidly. GFRP has because of the resin, not because of the fibers, they do have a property which is called glass transition temperature. Okay, which is the temperature at which the polymeric chains of which are made of which the resin is made, they start softening. Okay, and this transition temperature is roughly in the range for every manufacturer, more or less, around 100, 110 degrees Celsius, which means that in order to give a fire resistance to a structure, we need to protect the fibers. We need to protect the bars. Now, something very important. Imagine you have a slab, okay? And you have a fire below. Now, the fire will be affecting only the location under the fire. If the fibers, if the bars are properly anchored at the very end in areas where the fire may not reach the structure, then we can consider the bars still functioning, which means that we need to design properly in detailing, but the structure will not collapse under a fire. Let me give you also a very, let's say, simple and straightforward advice. If I were to start using GFRP today, I would certainly not focus to any structure where there is issue of fire. Why? Because we need to take into account several solutions to protect the bars, which may not make the bars effective and efficient, and I would say the right choice for that specific project. If we're looking at the adoption of GFRP in applications such as roadways, slabs on ground, marine application, port structures, and things like that, then, so basically in any application where fire is not an issue, then we can certainly have a very winning situation.
Thank you, sir. Then we have another question. Engineer Solly Basil, my chairman, nice chapter, sir.
Thank you, my NBC Southwest Professional Development Radar. Sorry, all other protocols duly observed. My question is, we've spoken about the safety aspect of the GFRP in terms of it is safer. We talk about the functionability, making us realize it's more functional, durable. Talk about the ductility and all whatnot. It's lightweight. How about the economy aspect of it? Talk about the comparative cost with our traditional steel.
Yes.
So can you speak to that?
Yes, absolutely. I honestly do not know the price of steel in Nigeria. That's I need to admit my ignorance. So I think I give you a reference though. In Europe right now, the cost of steel is about, because of the cost of energy and what is happening everywhere, is about between 750 and 800 euros a ton, okay? Because you need to compare in volume and not in weight, because GFRP is 4 times lighter, you need to multiply this price, or whatever price you have in Nigeria for steel, you need to multiply by 4. So if you take 800 euros a ton, 750, you ended up around, let's say, 7 times 4 is 28, 8 times 4 is 32, you ended up around 3,000 euros a ton. Right now, the cost of steel, the cost of GFRP is roughly 30, 25, 30, 35% more the cost of steel. But there is a big importance, there is a big aspect which is very important. You need to remember that the price of a structure does not depend only on the cost of the material itself. It depends upon how much time you spend building the structures. It depends how durable that structure is going to be, how much maintenance you need to do on the structures, and also the life cycle assessment of the structure. The beauty of GFRP is that once you want to demolish the structure, you can actually grind GFRP rebars and concrete all together and reuse the old reinforced concrete as a new aggregate for new construction. So it makes the solution very attractive, because that delta that I gave you in terms of extra cost of material is actually going to make probably 1-to-1 and 0 the final cost of the structure. So the final cost of the structure is not going to be 20-30% more, but that cost is going to be leveled within all the advantages that GFRP can give to the structure. And I can show you, I don't know if you want to go ahead with questions, if I answer to your question, or if we move forward, I will show you examples of structures being built, and I can give you a nice example of a bridge where, imagine, they plan to deliver the structures in 2 years, and the contractor, which is a worldwide recognized contractor, delivered the structure in 1 year only. So 50% saving in labor. You can imagine that the extra cost they pay for the material has been already paid off by the end of the construction works.
Thank you for your response. We also have another participant who wants to ask question. Engineer Akim Amda. You have the floor, sir.
Yeah, thank you, the moderator. Thank you, the presenter. My question is as regards one of your last statement. You said, of course, it's fiber and it's anisotropic. But in most cases where we use reinforcement, depending on the length that's required, we normally cut across the reinforcement, which means, based on what you said, that is not too good for the fiber material. So how do we treat this end whenever it is being cut? Or is it that we have to give specification to the manufacturer and they will manufacture based on the size you want to use for the construction? Thank you.
Thank you. Very good question. Usually, if the product is produced according to the standards, then I'm going to show you there is no issue in cutting the material. So when you cut the material, there is no problem in the surface of the bar being attacked or being damaged by the cutting. Okay, so there is nothing that, from a construction point of view on site, you need to take into consideration. What is very important is that you cut with a blade, okay? Not cut with scissors or anything that is trying to mechanically break the bars, okay? We need to be certain that we're cutting with a blade, a rotor blade. But apart from that, I think that's a tool that is available anywhere in the world in any construction site. I don't know if I answered correctly to your question or if I understood correctly.
Are you satisfied, sir?
Yes, yes, yes. Thank you.
You're welcome.
Then, Ego Daga, your question, sir.
Okay, I'm a lady. Good evening, everyone. All protocol.
Good evening.
Yeah, the question I want to ask, the last participants just asked the question, but there is another angle I'm looking at it. Yeah, I really like, I'm much interested in this. I like what I'm seeing because I'm doing a research. I'm currently doing a research that is related, But one thing I saw there, I even put in the comment section, that this is a challenge where you cannot bend on site. You cannot bend it on site. You said like up to 90 degrees, you can't be bent on site. And here in this part of the world, in this part of the world, we here in Nigeria, well, in our construction, where we consider labor, we always do look for things that are labor friendly, in the sense that when there are people that we call iron benders, is a form of providing jobs for these people where they will see what to do at the construction site. If like the normal one we use, the T-bars, the, their own job is to bend this thing. But what you're presenting to us is that it must be bent in the factory, meaning these people that do this kind of job, that their jobs will be taken away from them. That's the only challenge I see there. Even we, the engineers that are on site, just as the last person said, if we encounter these off cuts, how do we go about them? But you have already answered that aspect. But the only angle I'm looking at is taking away job from these people that we call iron benders, because they will not see, if we tend to start using this, they will,
Yeah.
we're taking away their jobs from them. So that's
No.
just what I see
Yes.
about every other thing is very good about this GFRP.
Thank you, Mrs. Daka. I think I understand perfectly your point, and I want to assure you also about one opportunity. We recently developed a code. It is the first one available in Europe for design, and again, it will be in your hands. Through the organizers of these, splendid moment to share with you. There is the possibility also of coupling the use of GFRP bars and steel, which means that we can use for straight reinforcement traditional GFRP bars, and let's say we need to build a column or we need to do anything with bend bars, we can certainly continue adopting steel. That's one option, and the other option is also to have bend bars that, again, we do not need to bend, but we can transform partially the work of these people in also assembling the bars, so preparing the cages for reinforced concrete. That's also another option. Again, absolutely, we do not want to take away labor. All the opposite. We want to make these people actually happier by adopting a material which is lighter, which makes their life easier, and which can increase their productivity. I understand your position. Thank you. There is another question. I see another hand raised from Mr. or Mrs. Moruf Olokian Yusuf.
Olalekan Yusuf, you have the floor, sir.
Thank you very much. One of my concerns have been addressed by the former questioner, by just the person that just asked question right now. My second question is just, is there any comparative study between the traditional reinforced concrete and the GFRP, especially from the point of view of stiffness? Because you said E is very low compared to RC. So I want to understand whether your organization has sponsored a research that compare the performance of traditional reinforced concrete on the deflection and ductility point of view. That's my question.
Yes, yes, very good question, and thank you for that. Obviously, because the actual stiffness of GFRP is less than steel in elements which are deflecting, which are subject to any moment and so to deflection, in order to account for the same deflection controls, we need to add slightly more material. It's not too much, it's not 4 times more. We are looking about, let's say, 20-25% more material in the section. This is true only for elements which are subjected to deflection. It's also true that because the material does not corrode, you do not have to worry for the same crack opening width of reinforced concrete as you would traditionally do with steel, because again, we do not need to be afraid of having, let's say, moisture or anything else entering the concrete. Having said that, there are applications, for example, slabs on ground or others, where, and all that what I'm saying is obviously supported by studies, so there is evidence, scientific evidence of that. There are these applications, for example, slabs on grade, where actually the adoption of GFRP can almost be brought 1-to-1. So let's say you have 10 millimeters bars, you can actually adopt 10 millimeters GFRP rebars. So you are really in a position where you can actually, adopt the same type of reinforcement. Do you want me to keep on going? Because, it's already 6:30 almost, 6:20 almost your times. I don't know.
Maybe you can just summarize and wrap up, sir, since we are done with the question.
Okay, so I keep moving, right?
Maybe in next 10 minutes, sir.
Yes. Okay. So I'll do very quick. I will literally scroll through these applications. Okay. Slabs on grade, for example, we can place the reinforcement directly on the ground. Okay. No need to protect the reinforcement, as you can see here. This is home construction in North America. Okay. So these are applications in North America done. Here we are in Saudi Arabia. Again, you see the reinforcement laid on ground. Elevated parking, Miami Retrorail, application by the sea. Here we are again in Saudi Arabia. Retaining wall and sea wall application for protecting the coastline. Here we are again in the United States. Pearl Harbor, for example, dock repair or balcony repair also. There is also a very interesting field of application in the repair of existing concrete structures where there is the need to repair the steel or replace the steel entirely because it's corroded. And certainly in those applications, the adoption of GFRP is very much supported. Here is a lighthouse along the coast of France in Europe. You see here the replacement. So this is an external jacketing of an existing concrete element that is done. You see the helicopter on the very right. That is transporting the material. These are substations, again in Saudi Arabia. Now we're just about approaching the opportunity of doing a large job in Scotland with the GFRP rebars. This retaining wall in Italy just being built. You see the bend shape that you see here in black are actually delivered again, like I was saying before, already bent, and then you see here the preparation of the cages on site. But again, you can see that the way the work is done is just like the one you would do with traditional steel reinforcement. Another interesting application is in drain concrete channels because of corrosion. And so certainly in those, there is an interesting field of application. This is the largest GFRP project in the world, is a Gisian flood channel. You see here the application. Again, in this case, the most of application is done with straight bars, and only on the side we needed the bent bars. Again, if needed, we can still couple straight bars with traditional steel reinforcement. We need to be aware, obviously, that everything that I said about non-corrosive, in the case we adopt steel, we need to take into account. Again, look at these numbers. We finally saved, despite an extra 10-15% in cost, we actually, because in that case they would have used coated steel reinforcement, we actually ended up saving 21%. And I think a big saving you need to see is in the labor and in crane, so in construction equipment on site. Again, Saudi is probably has a cheap labor, as probably as also Africa has. So, but by looking at this number, you can see that actually we are not going to take away the labor. We are actually making labor less less stressful for the people who work on the job site. This is the largest bridge ever built in the entire world, made with GFRP. Everything is done with GFRP bars. You can see the preparation of the reinforcement. And again, I just want to take you to the very last picture. We've saved 50% of the overall time of construction. So it's a big number. Now, let me briefly talk, because I literally have 3 minutes and I don't want to take you more of your time. Maybe we can plan another day when we can talk more deeply about design and code standards. One thing that I want to stress about the adoption of GFRP is the fact that we need to adopt, particularly because it's a new product and because it will be very difficult, not impossible certainly, but not as easy as testing and controlling traditional steel reinforcement. We need to adopt material which guarantees us that the properties that I state in the technical data sheets can be actually supported and guaranteed by a certification. And that's where the CE marking comes into place. CE marking harmonizes marketing conditions for construction products, removes the technical barriers to trade across countries, and enables free movement via unified standards and conformity. Outside Europe, CE marking for non-standardized products like GFRP rebars ensures third-party verification of testing and ongoing inspection. That means that once you receive the product in Nigeria, you can be certain only and only if the product is CE marked that that product has already been tested and is already being quality controlled by a third-party organization that is overseeing the production, in this case, in our case, located in either Saudi or North America, so that the product that reach Nigeria, in a sense, is guaranteed. Likewise, any other product that you may test locally. Very briefly, how does the process work? There is a document that is called EAD, a European Assessment Document, which is literally the list of tests and the protocol that the manufacturer has to follow. And the European Assessment Document has a general description of the construction product, a list of the essential characteristics that are relevant to that particular product. So any characteristic that it is important for GFRP glass fiber reinforced polymer bars to be tested is included in the document. And then there are the methods and criteria for evaluating the performance. So that means that also the method and criteria can actually be replicated in Nigeria if there is a third party or a national requirement for doing that. And also it reports the principle relating to factory production control, which is literally the most important thing. I will literally skip all this information because, again, these are testing, these are things that you can read out from my presentation. What I want to really go forward is that all the testing requirements is performed in ISO 17025 accredited laboratories, which is actually very important because, again, this is the ISO is international standards organizations, which guarantees the quality of the numbers which are present in the certificates. And the most important thing is actually the last piece of the process, which is the factory production control and the declaration of performance. Why I'm saying this? Because every CE mark product under these specific European assessment document, which is a 260023-00-0301, are under a AVCP 1+, which is the most stringent system available in Europe for construction products, which means that the product has to undergo a factory production control. There is testing being performed at a specific timing by the manufacturer. There is the assessment of the performance. There is the initial plant inspection by a notified body, and there is also the continuous surveillance and assessment and evaluation of the factory production control by a third party, which is the notified body, which means that there is an external body, official, agreed by the European community, that actually oversees the factory production control. And these are all the control plans that have to be done. You can see here all the information about incoming material, mechanical properties, glass addition temperature that we were saying. It reports also the minimum number of samples and also the frequency upon which we need to perform all these tests, okay? And if a producer that claims CE marking according to this standard does not perform this, let me tell you that there is a body that prohibits that person to continue selling that product. So you have to be in a certain way certain that the quality declared in the document, and this is the certificate in our case that we hold, is very recent because the testing has been extensive and require more than 2 years of testing to be performed. But also the very important thing is the declaration of performance. What is the declaration of performance? Is a sort of what is I call the performance identity card for the construction use. Why? Because it reports all the technical properties of GFRP bars that the company, in our case, the original composite company, takes as a sort of like binding contract with the market. So there is no possible way that we declare something that a third-party laboratory anywhere in the world following the same standard of testing can find differently, because otherwise we could be sued by the European community for having declared something not true. The declaration of performance has a specific format according to the standards, where you see the intended use of GFRP bars, the name of the manufacturer, the assessment and verification of constancy of performance plan, which is a 1+, the European assessment document, which is the reference document, the European technical assessment, which is literally the list of all the testing being performed, is a sort of like technical report of the product, and then is reported the technical assessment body and the notified body, and then are reported all the essential characteristics being tested by the manufacturer and the other remaining. And it's dated and is signed by the presence of the legal authority within the company. Because in the action of time, it's already 7:35 my time, 6:35 yours, I think probably there is no time for me to go over the design method that of the only code that we currently have available. I want to stress, though, the fact that within 1 month, 1.5 more months, by end of June, beginning of July, we will also have available a free, and I underline free software within European community to give to engineers following these standards, these design standards, for you to design reinforced concrete sections. The software will be available in English and will allow you to design with the GFRP according to these standards. Now, I understand that you probably will say, well, we design according to the British standards. Yes, and that's why I kind of referred everything to Europe. Why? Because the British standards, at the end of the day, are exactly. And once you will read the document, the Italian standards, which is available also in English, you will realize that a lot of, let's say, design approach, gamma factors, design code, and everything is very much alike what you have been used through the British standard. So you will find a lot of common points, common ground in the document. Now, I think I leave it to you, and I thank Emmanuel Inoquo that organized with you with the Chamber of Civil Engineers of Nigeria these wonderful evening and seminar. If you feel that there is the need to repeat these and maybe go deeper into design, you will have the slide, and we can certainly organize another session. And again, please feel free to ask me any question now, that even though the time is over, I don't know, I leave it up to you. Thank you.
Thank you, Dr. Paholo. We sincerely appreciate this. Distinguished engineers, you will agree with me that the time we've had this evening, it's worth the time. We sincerely appreciate this. And sincerely to you, we desire to have the design fashion, the basic testing, and all the procedure required. The Professional Development Committee of the institution will surely reach out to you, sir, for the final fashion. And I believe our people also will desire to also want to know and to have it. Thank you so much. Because of our time, and not to take too much time of our dear Muslim brothers and sisters who may want to go for prayer soonest, I will have this time, as our usual custom, we normally give a token of appreciation to our presenters. Why I request Engineer Ayinla to help us please display the certificate of presentation. I have the pleasure of the National Chairman, the NC, to call on the past National Chairman, Engineer Dr. Jang Tanko, who will help us to do the presentation certificate to our presenters. Thank you, sir.
Thank you.
Engineer Ayinla, please help us display the certificates. Let's have the two display if possible, or we take it one after the other.
Thank you so much. I really appreciate it. I truly appreciate it. It was an honor, really a pleasure. And again, I hope this is the beginning of of a great opportunity for innovating and making construction more sustainable in Nigeria, thanks to the adoption of composite glass reinforcement rebars. Really, thank you. Thank you so much. I really appreciate it.
My personal chairman, sir, Engineer Dr. Chang Tanko, please help us do the presentation proper.
Okay, thank you very much, Dr. Amosun. And we cannot thank our presenter enough. He has given us a technology that will really help to enhance our practice in this part of the world. I don't know whether my Reverend Senior Engineer S.A. Lawal is still on this call. If he is on this call, I will wish that he make the presentation, but if he has gone out, I will now quickly go into the presentation. Is he still on this call, Engineer S.A. Lawal?
Engineer Dr. Tanko Jang, God will honor you. Please go ahead and do the presentation. I appreciate. Please go ahead. I'm still on the call.
Thank you
go
very
ahead.
much, sir.
Thank you. God will honor you. Thank you.
Thank you very much, sir. Thank you for the honor.
Yeah,
because I cannot dare do that when you are still on the call. Having given me the opportunity, I would like to, on behalf of the Nigerian Institution of Civil Engineers, appreciate our presenter, Dr. Paulo Casadei. We want to appreciate you for sharing your invaluable knowledge with members of our institution. And this is what we call technology transfer. And this is our 31st technical session and professional development lectures. We appreciate you deeply. And we want to crave your indulgence that we will still have to bring you on board to go into the nitty-gritty of the design so that, of course, we cannot just do the practical aspect of it without the in-depth of the design. So we still wish and pray that you will still have time to share the knowledge in the design aspect with us in the near future.
Absolutely.
So we make this presentation to you with full of appreciation on behalf of the National Chairman, Engineer Dr. Ajanaku, as well as the entire ESCO and membership of the entire Nigerian Institution of Civil Engineers. We are so grateful. The certificate is hereby presented to you. Thank you.
Thank you. Thank you so much. I really appreciate it. Thank you.
Thank you, sir. Thank you, sir. I sincerely appreciate all our leaders, the PNC, and with all humility, appreciate our dear leader, Engineer Soliu Lawal, who has been with us since beginning, FNSCF Nice. I appreciate you, our PNC, sir.
Thank you very much.
Yes, sir. Thank you, sir. We equally have second presentation, the certificate for architect Emmanuel Inuojo, who opened the presentation. With your permission, my PNC, sir. Engineer Soliu Lawal, FNSCF Nice, sir.
Okay, no problems. Thank you very much, my NVC. On behalf of, we want to thank our brother in the built industry, architect Emmanuel Inuojo, for sharing your knowledge with us. We thank you very much. We want to inform you that we will still be inviting you, like Engineer Dr. Tanko Jang said. We'll still be inviting you later concerning this topic on ground. So on behalf of my national chairman, Engineer Tokunbo Ajanaku, FNSCF, NICE, PMP, I, Engineer Silawa, hereby on behalf of the institution and the NC, present to you this certificate of appreciation. Today, this day, 14th of May, year 2026. Thank you very much.
Thank you so much. I appreciate the NIC, and I can assure you this is just the first sprint of a long marathon. There is the need for design capabilities, local testing, and integration of GFRP design into BS 8110. We had a meeting not long ago with the American Concrete Institute, and they made us realize that if we go ahead and do the integration, we'll actually be creating history for even the other European countries, including England, to come and study the Nigerian system of how we are able to integrate GFRP design into BS 8110. So like I said earlier on, it's a sprint, the first sprint of a long marathon, and we are all at the door of making history by bringing GFRP into BS design. Thank you very much, and of course we'll continue the conversation with the executives of the NIC, and of course definitely we'll need to do another meeting where we'll elucidate more on the design and the testing capacities. Thank you so much. I'm happy to be here.
You're welcome, Architect Enwicho. You're welcome. Thank you.
Thank you, sir.
Thank you, my leaders on this call.
You're welcome.
Thank you,
just a
engineer.
moment, Engineer Dr. Grace.
Yes, sir.
Please, just following what Architect Inoh just said, instead of the integration with BS 8110, which is almost extinct now, can you have it done with Eurocode 2 so that we're in tune with current trends of code development? Is it possible?
That is very doable, and what that actually means, we'll have to be taking this conversation at a very top level as policy change as a country, or have two design codes exist side by side, which I believe there will be no issues to that. And that is why we have started a conversation with the Nigerian Building and Road Research Institute to not only develop local testing capacity, but also be an advocacy at the federal level, and to make Nigerians know that we have this material in the country. We are trying to bring the material in the country, and we're also trying to make sure that we have a design capabilities as well as teach this in our universities, so that those in school now will not leave the school before they hear about GFRP like us. So those collaborations are ongoing, and yes, we can actually make it exist side by side with BS, but at the same time, because there is a point of inflection where we might have to use the regular steel with GFRP. That was why I spoke about integration. You know, just like one of the engineers said earlier on when she was concerned about the iron benders and not having jobs, and I put in the chat that actually the GFRP can be used with the traditional steel, in the sense that the bending schedule can be done with the regular steel. So the iron benders will still have their work, you know, on the site, and we're not taking anybody's job away. So every possibility is on the table. It depends on how we want to take the directions.
Thank you, sir.
Thank you. The only final fear is that everything will have to be referred back to your factory, even minor bendings. You know, if I heard the lecture well.
Yeah, which is why I said we don't have to do that, sir. We can do all our bending schedules locally here using the regular steel. And that is where I said the design for BS 811 might have to exist side by side with the one for GFRP to make sure that marriage is a successful one.
So how do you use the GFRP for column starters?
Say again, sir, I didn't get that.
Column starters that must have a
that is where we use the regular steel for the L shape. So all the bending elements or bending schedules can still be done with the regular steel if we want to avoid having to manufacture all the bends from the factory in Europe.
Okay, thank you.
Yes,
thank you. So,
you're welcome, sir.
All right,
Yeah.
Dr. Green, go ahead.
My DNC prof, sir. Sincerely, all the contributions, they are towards enhancing learning, which